In this section, we're going to learn about Green's theorem. Now, I'm going to start by stating Green's theorem, then we'll try to understand it and we'll gain some intuition on why it's true. It's actually a pretty straightforward idea once you understand the basics of it. Okay? So Green's theorem, let's let D be an open, simply connected region. With a boundary curve C. That is piecewise smooth that is a piecewise smooth simple closed curve oriented counterclockwise. Okay. So we're going to take a vector field. So let F be a two-dimensional vector field. Let's give it components P and Q. So P and Q are going to be functions of X and Y. Okay. Does this be a vector field? Be a continuously differentiable vector field. Over our region. Then we have the following. The integral over curve C of f dot dr, so that's the vector line integral over curve C, is going to be equal to the double integral over the full region D of the scalar curl of f. Okay, so a few things to say here. Note that curve C is a simple closed curve. The closed curve part is pretty straightforward. Okay, it means that it comes back to itself, right? It closes off a shape, right? It's not just a line in space, but it comes back and closes itself off, right? The simple part means that it doesn't make a loop or something. All right, so we have a simple closed curve C. Now, because it's closed, we sometimes have a special notation that we use for integrals when we're integrating over a closed curve. To emphasize the closure, we'll often draw a little circle over the integral. That means we're integrating over a closed curve because there are special properties that happen with closed curves, so sometimes we want to emphasize that. Now, if we left that off, the integral is exactly the same. All that circle does is emphasize that the curve is a closed curve. If that circle isn't there, the curve's still a closed curve. The integral is still what it is, but it's just not emphasized. Okay? And then over here, I have the curl of f. Now, f is a two-dimensional vector field. So when we take the curl of a two-dimensional vector field, we are taking the scalar curl. Okay, so this is going to be the scalar curl. Remember, to find that scalar curl, you treat you embed your vector field in 3 dimensions. That gradient operator is the partial x, partial y, partial z. And the vector field itself is p, q, and then when we embed it in the third dimension, we get 0 for that third component. All right, so if you actually take the curl here, you get 0, 0, and then the partial derivative of q with respect to x minus the partial derivative of q with respect to y. And because these two components will always be 0, when we take the curl of a two-dimensional vector field, we identify it with just the third component. Okay? So this is our scalar curl, just that third component. All right? And I'm sorry, I've written it wrong. It's qx minus py. Okay? Partial derivative of q with respect to x minus partial derivative of p with respect to y. Okay? So another way I could write this equality here, is the integral of the first component with respect to x plus q dy. That's an equivalent way to express the line integral. Or I could write it as the double integral over region D of the scalar curl of f, which would be qx minus py. Integrated over the area. Okay, so these two statements mean exactly the same thing. We're just writing them a little bit different. All right. Now what it's doing is we have some region D. Okay, we have some region D. C is the boundary of region D. C is the boundary of region D. Doing a very good job. Okay. That's curve C, and it's oriented counterclockwise. So what Green's theorem does is it relates how the vector field is integrated over the curve C with the scalar curl of the function over the full region of the interior D. Okay? By the way, this integral here, the integral of the vector field over curve C, that's what we call circulation. When we have this closed integral here, it's how much the vector field is moving along that path, is circulating along that path. Okay, now I haven't drawn the vector field here because it would get very busy, but we could kind of imagine that, you know, maybe a vector field might do something like this. Okay, and you could see how in general we would circulate along that path. Okay, all right, hopefully we kind of understand what we're talking about now. I'm not going to do a full formal proof. It's kind of complicated, but the essential idea of it is pretty straightforward to understand. All right. So we've learned how to think about curl in a discrete way, right? If I think about a point, kind of draw a box around that point, then the curl at that point we can estimate it with the circulation around that little box. Okay? The curl measures how the vector field circulates around the box. Now, let's kind of imagine that our region D, the interior of our region is full of boxes. Okay, full of these little boxes. I'll try not to draw too many. Okay. Maybe just one more over here. Okay. So imagine all of this area right here. That's D. That's region D. Okay. And then the boundaries of these boxes that is our boundary C. Okay. So let's think about the curl in all these boxes, circulation around every one of these boxes. Okay. All right. So if we were to kind of add up the circulation every one of these boxes, it represents the curl. And so it is similar to integral d of the scalar curl of our vector field. Okay. All those little boxes added together. We're just adding up all the little curls. Now, I've drawn them as discrete boxes, but imagine these boxes get smaller and smaller and smaller and smaller, and in the limit, they're just a point. That's what we're doing here. We're taking the curl around each point, the infinitesimal circulation around a point. And we're adding them all up for every point in our interior region D. Every point in the interior region. Okay? Now, the boxes give a good idea of what's going to happen. Okay, so say I add the curl of this box, the circulation in this box, to the circulation in this box. Okay, what's going to happen? Well, you know, that and 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 that. All these little elements get added together. All right, but notice along this edge, we are measuring the circulation on the right side going down, but on the left side going up, but it's the same edge, right? So because we're measuring in opposite directions, maybe one would be positive, which would mean the other one, since I'm measuring it the other direction, it'd be the same amount but negative. And so they would cancel. Okay, those two sides would cancel. Similarly here, this box here, okay, the top edge here, we could see we're measuring the circulation as we go left, but we're measuring the same circulation along the same edge going right, so we're measuring the same amount, but just in opposite directions. So we'll get opposite signs. And so those will cancel also. So every time we share an edge, we're measuring the same circulation, but in opposite directions, so they will cancel. That's going to happen with every single shared edge. Okay? If we cancel all those, what are we left with? Well, we would only be left with the circulation measured on the edges that aren't adjacent to another square, another box. Okay? Those on the boundary. So if we think about that, that's just how much the vector field is flowing along the boundary. Okay, which is exactly the circulation along the boundary, the circulation along that outer edge C. That's all that remains. And so it must be equal to the line integral of the vector field over the boundary C. Okay, measured in the counterclockwise direction. All right, so if we add up all those little curls on the interior, everything cancels except what's on the boundary. And so it's the same as the circulation along that boundary. Okay, so that's the idea of Green's theorem. Let's take a look at an example which shows us just how useful Green's theorem can be. All right, so here we want to evaluate a vector line integral over curve C, where C is the boundary of the rectangle with these vertices. Okay, so kind of sketch it out. X, Y, so 0, 0 is right here. We have 1, 0. Like make it a, well, no, I'll put it right there. 1, 0, 1, 5, 2, 3, 4, 5, and 0, 5. So we're getting this rectangle here. We want to integrate the vector field along this rectangle, along the boundary of this rectangle. Okay, that's going to find the circulation of this vector field over the rectangle, over the boundary of the rectangle. All right. Now, if we had to do this using vector line integrals, it would be a little unpleasant. All right, because here, let's specify what our vector field is first, right? The first bit here, that's our x component of our vector field, xy squared. And x cubed, that's the second component of our vector field. So we want the integral over C of this function f. Okay, vector line integral. This is exactly the same as this. We've just written with a little bit different notation, right? The problem here, of course, is that if we were to try to integrate over the curve, each one of these pieces we'd have to parameterize separately. When we're doing a vector line integral, we need to parameterize curve C. But curve C here is kind of 4 distinct pieces, right? The easiest approach is to parameterize each of these pieces separately. Maybe this would be our first parameterization. This bottom edge, the right edge would be R2, our second parameterization. R3, R4. In fact, let's actually just call it C1, C2, C3, C4. Have to break these into pieces. Okay? And so instead of integrating over C, we'd integrate over C1, and then over C2, and then over C3, and then finally over C4. We'd have to do 4 vector line integrals. And while each one on their own isn't especially difficult, it's just a lot of work, right? We'd have to do each one of these sides individually. Okay? Now, let's apply Green's theorem. Green's theorem applies because we are integrating over a closed curve, right? Closed curve comes back to itself, closes off the shape, right? So according to Green's theorem, if we're integrating over a closed curve and we meet all the other requirements, instead of integrating over the boundary, we could integrate the scalar curl of the vector field over the interior. And the interior region here is really nice to integrate over. It's a rectangle. That's as easy as it gets for double integrals. Okay? So what we want to do here is find the scalar curl. Remember the scalar curl, if f is equal to a vector with components p and q, then the scalar curl is going to be the derivative of the second component of the field with respect to the first variable x minus the derivative of the first component of the vector field with respect to the second variable y. Right? So in this particular case, what that means is if I look at the second component of the vector field f, we're going to take the derivative of that with respect to x. And then subtract the first component of the vector field with respect to variable y. Derivative of the first component of the vector field with respect to variable y. Yeah. Okay? Integrated over the area. So I get 3x squared minus 2xy. And then just integrate it over region D. This is just a double integral. Okay, so I could slice it up either in the vertical direction or the horizontal direction. Maybe I'll do it in the horizontal. So if I slice it up this way, that means that I'm letting the x change. I'm holding y fixed. So I'm going to integrate first with respect to x. Okay, where x goes from this edge to this edge, right? This edge to this edge. And so, based on my vertices, I'll go from x equals 0 to x equals 1. And then I integrate with respect to y, collapse the shape in the x dimension. And I go from y equals 0 to y equals 5. This is going to be much easier to integrate than having to integrate all 4 of these little line integrals, parameterize each edge of that rectangle. Okay, so using Green's theorem, we can simplify the integration. Let's take a look at one more example. Here we want to evaluate the line integral of a vector field over curve C, where C is the boundary of the region between the circle of radius 1 and the circle of radius 4. So quickly draw it out. So circle of radius 1, circle of radius 4. Okay, so C is the boundary. Okay, so C is the boundary. And the region itself is this region here. Okay? So we want the integral over the boundary. So again, our vector field f, let me write it out first. The first component is y cubed. The second component is negative x cubed. Right? Now, we want the integral over the boundary. The line integral of vector field f over boundary determined by curve C. Now, we could do it directly. It wouldn't be too bad, but we'd have to break this into 2 pieces because we have kind of 2 segments to our boundary. We have the exterior circle, right? We have the exterior circle, and we have the interior circle. We'd want to break those into 2 distinct pieces, so we'd have to do 2 distinct line integrals and then add them together. Instead, let's integrate over the interior using Green's theorem. We can do that because the boundary is made up of closed curves. Okay? So instead, we're going to integrate the scalar curl of function f over the boundary. Okay? Now, the scalar curl of f, and let me derive the scalar curl of f just so you can remember how to do that. Okay? For the curl of f, if we embed this in 3 dimensions, then the curl of y cubed comma x cubed, let's see, and that should be a negative x cubed, shouldn't it? Negative x cubed, comma 0. We add the 0 because we're embedding it in 3 dimensions. Get ijk, partial derivatives with respect to x, y, and z, and y cubed negative x cubed 0. So if we take the curl, we're going to get 0, and then this will also be 0 because I'm taking the partial derivative with respect to z, and there are no z's here. Okay, so the first component here is 0. The second component, the j component, partial derivative of 0 is 0 minus partial derivative of y cubed with respect to z. Again, there are no z's in this expression. We hold y as constant. Derivative of a constant is 0. So this is also 0. Okay. Finally, the k component, last component of our vector, partial derivative of negative x cubed with respect to x, minus partial derivative of y cubed with respect to y. Okay, so that's the curl of the vector field embedded in 3 dimensions. When we pull it back, we say the curl of the 2-dimensional vector field f is just the non-zero component of the vector, just the scalar component of the vector. Okay, that's true whenever we have a 2-dimensional vector field. The scalar curl is a scalar value. If f was a 3-dimensional vector field, remember the curl is a vector. Okay, so that's what we plug in right here. Okay, so partial derivative with respect to x of our second component minus partial derivative with respect to y of our first component. We're integrating over region D. All right, so partial derivatives are easy to take. Partial derivative of negative x cubed is going to be negative 3x squared. Partial derivative of y cubed is going to be 3y squared. Okay. Now, based on region D, which would be the interior here, this region right here is D. It's an annulus, okay? The interior of one circle and the exterior of another circle. The easiest approach here is going to be to use polar coordinates. So let's use polar coordinates. So I'm going to factor out the common negative 3. Since it's a constant, I could pull it out of both integrals. I'd be left with x squared plus y squared, right? This is negative 3 times x squared plus y squared. And x squared plus y squared is r squared. So if I'm converting polar integrals or polar coordinates, this is a great way to go. X squared plus y squared is r squared. And since I'm converting to polar coordinates, I also get another factor of r, right? And then let's integrate first with respect to r. Now r will go from, no matter where I draw my radial slice, it'll start, I start counting it at the edge of the inner circle, and I end at the edge of the outer circle, no matter where I slice it. Okay. So it will start when r is equal to 1 and end with the radius is equal to, and you know what, I'm just realizing I drew it wrong. This is the radius squared, right? So the radius should be equal to 2. Okay, not 4. So radius from 1 to 2. Okay. You understand what I mean, right? Just, mentally correct the image in your head. Okay. And then integrate with respect to theta. We want to go all the way around. So if we integrate all the way around, that's going to be 0 to 2 pi. And so I just need to integrate r cubed, where r ranges from 1 to 2, and then theta ranges from 0 to 2 pi. Okay? And I'll leave you to do the rest. We're going to look at one more theorem before we finish off this section. This theorem has a couple of different names. Sometimes this is called the flux form of Green's theorem, or the normal form of Green's theorem. Your book likes to call it the flux form. Okay? I think more commonly, though, it's called the divergence theorem. It's just a special case of the divergence theorem, restricted to only 2 dimensions. Later on in the course, we will talk about the divergence theorem for 3 dimensions. But in essence, it's the same idea of what we're going to talk about here. Okay? So let's let D again be an open, simply connected region. With a boundary curve C, that is a piecewise smooth, simple closed curve. So far, the assumptions are the same as the Green's theorem that we originally learned. Okay? Again, let's let F be a 2-dimensional vector field. Let's have it have components P and Q. Be a continuously differentiable vector field on, say, over D. Then, actually, let me say one more thing. Let N be the outward unit normal vector to the curve. Then the integral over curve C of the vector field dotted with that unit normal vector is going to be the double integral of dO of the divergence of that vector. Okay? All right, so let's understand what it's saying here. Just as before, we have some region. Now, D is the interior of the region, and C is the boundary around the region, the curve around the region. Okay? Now, what we're doing is we're taking the dot product of F with the outward unit normal vector to curve C. Okay, so what do I mean by the outward unit normal vector? I mean that at every point along the curve, N is normal to the curve and pointing outward, away from the interior. Okay, at every point along the curve. Okay, so we're taking the dot product of our vector field at that point with the vector normal to the curve at that point. So what we're doing is we're saying how much, what is the component of vector F that is normal to the curve, okay, to the boundary. And then we're adding it together, okay? What we're finding here is called the flux. The flux is how much the vector field flows out of the region, right? So for example, let's say we have some that our vector field kind of looks like this. At this boundary, okay? What this is measuring is it's measuring how much of that vector field at each point along the boundary is flowing out directly out of the boundary, right? There's a portion, maybe change the color on this. There's a portion here that flows out of the boundary. That's what we're measuring. There's also a portion that isn't flowing directly out of the boundary. It's flowing parallel to it. We're measuring how much is flowing out, right? If we're going the other direction, then we'd be negative and it'd be measuring how much is going in. So it's the flux. The flux. The measurement of how much of the vector field, actually a measurement of the net flow of the vector field. Out of the region D, right? If you're going to flow out, you have to go through the boundary. And so that's what we're measuring. We're measuring the flow out of the boundary. So if we're flowing out of the boundary, if the net flow is out of the boundary, then this flux calculation will be positive, all right? But it could also be negative. If it's negative, then the net flow is going into the region, all right? Generally, there's probably going to be some flow into and some flow out of. We're just calculating the net flow. So we kind of put it all together. Is more flow going out or going in? Okay. Now, what this is saying is we could look at just the flow through the boundary, the flow that is normal to the boundary, flow that's going directly out of the boundary. Or instead, we could look in the interior and we could kind of measure all the flow together in the interior. And by putting it together, we could figure out how much of the flow is going into the region and how much is leaving through the boundary. All right, so let me draw you a picture similar to what we did before to give you a sense of what's going on. So just recall, we can draw a picture here of divergence of F. We have a point here. Then our divergence, if we kind of discretize it, come to that point a little better. If we discretize it, then what it's doing is it's going to measure how much of the flow is going through each of these edges. Okay, so if we imagine a little region made up of these squares, okay, so imagine that this is region D. All of this is region D. Okay, the boundary here is the boundary of our region. So if we measure all these little, the divergences at all these little points, and then we added them together, notice that very similar to how we calculated it for the circulation, for our other form of Green's theorem, okay, that with adjacent cells here, adjacent boxes, we're measuring the flow of the vector field out of this box, which would be going to the right, but in this box to the right of it, on the same edge, we were measuring the flow to the left. So a positive flow here would be counted as negative over here because we're measuring it in the other direction. And so when we put them together, if we were to add both of these cells together, these would cancel. Okay? And the same thing happens down here. We're measuring the same flow but in different directions. So when we put them together, they cancel because one would be positive while the other negative. That happens with all these adjacent edges. So just like before, the only edges that we're left with are the edges on the boundary. And so all we're seeing is the flow out of the boundary edges. And so that's how we're getting what we're getting. We start by computing the divergence for every point inside our region. Okay? And that's just like computing the divergence for each one of these boxes, but imagine the boxes get smaller and smaller and smaller and smaller until they're infinitesimal. And so we're calculating the divergence at each infinitesimal point. Okay? And if we add them all together, then most of the contributions of those from each one of those points will cancel. All right? Every box it's next to, every point it's next to, the contributions cancel. The only time it doesn't cancel is when you have an edge not next to another cell. So the only result we have is what's left happening along the boundary, which would be the flow of the vector field through the boundary in the direction normal to the boundary. Okay? That's the idea behind this flux form of Green's theorem, or the divergence theorem. Let's take a look at an example here. We want to use Green's theorem to calculate the flux through curve C. Okay, where the vector field F is defined by this, and curve C is the boundary of the region enclosed by y equals x minus x squared and the x-axis. Okay, so just a couple words on notation first. Notice they're using a lowercase n when I just showed you the formula, I used an uppercase N instead. That's okay. It means the same thing. Notation may differ from mathematician to mathematician or textbook to textbook. Both of these mean the outward-oriented unit normal to the boundary curve. Okay? It means exactly the same thing. They've just chosen to use a lowercase n. The textbook likes to use an uppercase n, which is why I use that in my notes. Okay? Also, notice we do not have a circle here to indicate it is a closed curve. That's okay. The problem isn't any different. They just haven't used that notation. Putting this on or taking off doesn't change the math at all. It's just helpful if you are dealing with a closed curve to include it. That way we know it's closed. But if I leave it off, that doesn't mean the curve isn't closed. It just means that I haven't specified it. Okay? All right, so let's see what our boundary looks like. So I have 1x minus x squared. So if I find the x-intercepts, I get x equals 0 and x equals 1. Let's put 1 right there. Okay, I know it's pointing downward, right? This is a parabola that opens downward. And because the x-intercepts are 0 and 1, the vertex must be at 1/2, right? A parabola is symmetric. So if I plug in 1/2, I will find the x and y values of the vertex. So the vertex, if I plug in 1/2 for the x, 1 times 1/2 minus 1/2 squared, I get 1/2 minus 1/4, which is 1/4. So the vertex occurs when x equals 1/2 and y equals 1/4. So right about there. So I want C is the curve that bounds this region right here. Okay, let's draw that a little bigger so we can really see. Okay, this is the region, and the boundary is curve C, because C is the boundary of the region enclosed by our parabola and the x-axis. Okay, so that's the region that's enclosed by both. Okay, we could just do the line integral. So we want the integral of f dot n over curve C. That means we want the flux of the vector field through the boundary. Through the boundary. Okay. There are a couple reasons why that might be hard. First, finding the unit normal to the curve, that's going to be a little unpleasant. All right. But perhaps even worse is I'd have to break it into two integrals, right? I've kind of got two sides here. I'd have to describe my boundary with two different sides. So rather than doing that, we can use the flux form of Green's theorem to integrate over the interior instead. And I'd just be integrating the divergence of that vector field over the interior. Okay. Okay. So we're going to need the divergence of our vector field. So here's our vector field right here. So let's take the divergence of that. So f is equal to root x plus 5y comma 3x plus 5y. The divergence then, remember, it would be the partial derivative of the first component with respect to x plus the partial derivative of the second component with respect to y. And so I would get 1 over 2 root x for this first derivative, and plus 5, which is the second derivative. Okay, that's great. That's the divergence of f. That's what's going to go in the integrand. All right. Now, I could either integrate first with respect to x, slice it up horizontally, or I could integrate with respect to y. I think y is probably a little more natural in this case, so let's integrate first with respect to y. Okay. For each slice, if I integrate with respect to y, each slice starts along the x-axis, y equals 0. So y equals 0. And each slice ends on the edge of the parabola. Okay, the edge of the parabola was y equals 1x minus x squared. So y equals x minus x squared. Okay, once I have y done, I can collapse that dimension and integrate with respect to the remaining variable x. Okay, and this goes from x equals 0 to x equals 1. My x-intercepts, which I already found, right? X equals 0, x equals 1. All right, so that's how you would set up a problem like this using the flux form of Green's theorem.